Welcome to the CFE Media and Technology Education session, Applying Control Concepts to the Adoption of Industry 4.0, sponsored by Honeywell. I'm your moderator, Mark T. Hosky with CFE Media and Technology. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session examines digital transformation, Industry 4.0, and Industrial Internet of Things, and looks at how control theory and control principles can be applied to human systems. Learn from an application that matches Laplace transforms with the Toyota production system and uses Industry 4.0 low-cost feedback loops to do it. Here is a list of learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you would like to take notes within the session, click on the left panel labeled Notes to do so. Remember that the session will be made live at 10 a.m. Central, 11 a.m. Eastern. Question and answer session starts immediately after the presentation ends. Want to take the session again? No problem. The session will be available on demand. If you're experiencing difficulties, please log out and back into the session to continue. Here is some information about obtaining an approved PDH for today's session. Now we'll have a brief word from our sponsor. Today's speaker is Dr. John Carrier, Senior Lecturer, MIT Sloan School of Management, Systems Dynamic Group. I'm your moderator, Mark T. Hosky, Content Manager, CFE Media and Technology. Dr. Carrier works with senior and frontline managers on improving manufacturing and business processes and serves as an on-site, hands-on coach in support of projects. His research focuses on the competitive advantage of synchronization of operations within supply chains. He has more than 20 years of experience in a variety of corporate, entrepreneurial, and consulting environments. Dr. Carrier also handles due diligence, post-merger integrations, and financial analysis and improvement. Prior to joining Arsenal Capital Partners, he was employed by Grace Construction Products, Bain & Company Incorporated, and Supercool LLC. Dr. Carrier holds a Bachelor of Science in Chemical Engineering from the University of Michigan, a PhD in Chemical Engineering from MIT, and an MBA from Harvard Business School. John, please go ahead with your presentation.
Great. Thank you, Mark. And I'm here to discuss today the greater role for control systems engineers granted to us by Industry 4.0, which technologies are changing the paradigm of organizational structure and operations. This paradigm change is based on control concepts: better, more, and faster information loops, greater resolution, increased visibility, and better real-time modeling simulation. And Industry 4.0 is extending the control concepts to the entire organization. This is a classic diagram from James Rasmussen, looking at how safety and unexpected events propagate through an organization. In the traditional system, looking at control, both of quality and of error propagation, we typically look at the horizontal pathway of moving from root cause through the causal chain and the critical event, and then the expectation or outcome, whether that be a positive outcome or a negative. And in the extended role, we're actually looking at how over time, when that set of events is repeated, how those defects do or don't propagate up through the direct staff, the management, the company, and all the way to government and regulation. And traditionally, it wasn't possible to collect all this information and act in a real-time manner. But today, thanks to the low-cost computing power and sensors of Industry 4.0, we are moving into a new era. That's not only going to allow us to make processes and systems more productive, but also make them more resilient and safer. And just to show this diagram, this is actually being realized through full organizational teams based on real-time instant communication, which is, of course, feedback. So in a traditional organization, you'll see the functional layout here with the CEO and the functional silos. And the modern theory for designing organizations based on agility is not simply to replace the existing structure, but to make up to 20 to 30% of those functions to be agile, communicating and solving ambiguous problems throughout the organization, which we can see on the bottom line is showing this, again, ubiquitous feedback that's passing through the organization and breaking down functional silos. And you will notice the analogy of this diagram to a classic feedback control diagram with information loops. And although there's this tremendous opportunity to apply control concepts to the wider organization, there's tremendous confusion regarding the current techniques and language around many of the tools used by control engineers to improve system performance and risk profiles. So for instance, I show here on the left many of the tools that are currently being used for the redesign and operations of organizations: quick changeovers, lean operations, agile, inventory reduction, Kanban. And although these look like a set of independent tools, viewed from a control theory insight, they can all move from individual toolbox approach to an actual systematic approach to, again, create systems that respond more agilely and resiliently to changes in the external environment and actually learn. So first, I'd just like to test your systems thinking. And I'm going to give you an example from Amsterdam. And back in the 1970s, during the energy crisis, the Netherlands conducted a very detailed energy usage study. And they discovered something fascinating. People that lived in houses directly on the canal used 30% less electricity than those who didn't. And the question is why? Well, we can first take ourselves through a normal type of structured problem-solving basis, and we start to isolate the elements, and we realize that the people who live directly on the canal are really the same as the people who live 1 or 2 blocks off. So it's not the people. So what is different? When we actually look at the structures, if you live on a canal, your number one concern is probably flooding. And houses directly on the canal don't have basements, unlike their neighbors. So here's a one-to-one correlation. But how does the lack of a basement actually influence people's usage of electricity? Well, it turns out normally in the 70s, the basement is where you put the electric meter. So if you don't have a basement, that meter was instead placed in your foyer near the front door. So now we're starting to unravel this behavior, and we see that so what's driving it is real-time observation of your electricity usage actually reduces it by 30%. And the point that's fascinating here is this was a missing or slow feedback loop. And simply by providing this information in real time had an incredible impact on the way people behaved in that system. And so a key part of this talk is that the world is filled with missing feedback loops. This is a causal loop diagram, which is a classical way of looking at all the connections, flows, and feedbacks between any system, be it a chemical plant a mortgage loan process, or a government regulatory system. And you'll see that the figures in the diagrams are the same across those systems. You'll also notice that many of these lines indicating positive and negative feedback loops are not consciously in the minds of the people within those systems. So with a better understanding of control systems and the actions of feedback loops, we can take our experience as control systems engineers and help engineer a better running organization. And armed with the technology of Industry 4.0, we can actually create much more affordable solutions that weren't possible even 10 years ago. So whenever we're trying to improve a system, our systems are large, they're expensive, we simply can't replace them. We're typically working with brownfield systems, whether it be in chemical plants, discrete manufacturing, or any other sort of organization. And one of my colleagues in the System Dynamics group at MIT looked at these systems and came up with 12 intervention points where a small interaction can actually lead to large performance changes and lead to better system performance. And while I'm not going to go through all these 12 intervention points, I want to highlight a few because they strongly reflect feedback control system concepts. So one of those is the length of time delays relative to the rate of system change. And we all know as control systems engineers how difficult it is to deal with delays, also known as dead time. So the ability to actually go in and, one, be aware of these delays, and two, reduce these delays through the application of new technology and modeling actually can drive tremendous system change, but it requires someone with the knowledge of a systems control engineer to do that. Related to that is, of course, the concept of negative feedback loops and relative to the impacts they're trying to correct. And I think, like the example we saw with the Amsterdam electricity usage, there are a lot of slower missing negative feedback loops that we are now going to be able to affordably install in our systems. What's driving this? Well, there's a rapid drop in the cost to implement a control loop. And anyone who has access to Amazon can essentially, for less than $100, buy a computer chip and a set of sensors and can wire up a feedback loop real time to the internet in about 15 to 20 minutes. And essentially, the cost of sensors has dropped by several orders of magnitude over the past 20 years. The size has also dropped. And what does this actually mean for our current systems if we could actually afford to put a fast feedback loop anywhere we desired and use that to communicate that information across the globe as needed? So we've talked about how this rapid change in the cost of communication and information technology has really opened up and expanded the toolbox that control systems engineers have. And now it's time to look at the fundamental control concepts that we can use when we start to think about not only designing and redesigning physical operations like chemical plants, but also designing the organizations and systems that run around those systems, including people. And let me tell you what those 10 control concepts are: observability, controllability, the overall time constant, stability, the inventory and dead time, the 3 types of control loops, systems, models, and data, inverse response, and of course, the Laplace transform for how people behave, which is Lewin's formula, and then ultimately the fundamental principle of synchronization. So let's look at observability. So when we think about this concept in a control system space, it's the ability to detect the state of a system prior to its consequence. And the classic example is riding a bicycle with your eyes open, because you can look ahead of you and see that the road or system is changing, and your observation occurs before the consequence. So unless you're able to observe the change in system before the consequence, you have no ability to change the outcome. And where technology can help with this is in the example of a bicycle. If we had a bike lamp, it pushes out our observability. If we're in a chemical plant, adding real-time sensors, including vibration and ultrasound to our rotating equipment, is another example how we're getting early signals that improves our observability. The next concept is, just as an example, what occurs if we don't have that observability. Here's an unfortunate example from Texas City in 2005, the isomerization unit. The consequence of a lack of observability was 15 fatalities, major damage to the physical asset, and finally led to industry change. And here was the loss of observability that contributed to this tragedy. Essentially, they started with 3 sensors for measuring level, and they were down to 1 sensor that's saturated to 9 feet top reading. Unfortunately, the column actually filled to over 150 feet, and this lack of observability resulted in this disaster. And what are some of the technologies that can help prevent this loss of observability? Well, first, aside from ubiquitous sensors, in this case, there's also better predictive maintenance and using advanced tools like machine learning and digital twins to indicate that our sensors are failing or that we're losing observability. And also education. The reason why we're going through many of these fundamental concepts of control and putting them into common understanding terms is so that we can extend our knowledge as control systems engineer to people that actually work in the plant. Now that we have observability, the next concept is controllability. And the definition here is the ability to change the current state of the system to reach a desired state or present an undesirable one before the consequence. So back to our bicycle example, this is not only riding the bicycle with our eyes open, but also having a set of working handlebars. So you can see on the graph in the left, if we're able to make our observation and take our control action before the consequence, we have a good system. And here's a place where augmenting our existing systems with technology can actually improve the speed of our control actions. And some classic examples are automated revalves, robots, where they're needed. And what happens when we have a loss of controllability? On the left is the Deepwater Horizon, and the consequence of losing controllability in that scenario was 11 fatalities, major damage to physical assets, and again, a major physical change. And the contributing factors to that were blowout preventer actuator failure, and the technology that could have helped monitor that loss of controllability include remote monitoring, predictive maintenance, machine learning, and the use of digital twins in education. And in organizations, it's often a challenge to balance the observations with the control actions. So for instance, we all know when we're running a control system is taking many observations, you're only allowed 1 control action. This happens on the discrete equipment. It also happens with people. Here we are looking at a classic multiple input, single output system, and what here could go wrong. So being conscious of our balance between observations and control actions is another core insight from control theory that we can actually apply to the operation of organizations. Now, the next key is response time. And of course, we're all conscious and aware that one of the key elements of designing a control system is understanding the natural time constant of the system we have and thinking about how we invert that so we provide it with a time constant that meets the needs of the customer. And the definition of the time constant is really the time it takes the system to reach a desired output once we have the change in input. So an example from our bicycle again is the time it takes to avoid a pothole once you've actually seen it while riding the bicycle, and you can think your way through the steps. And really all the technologies apply to response time. And just as a great quote that extends this concept from control theory to actually the running of organizations is this great quote from Jack Welch. If the rate of change on the outside exceeds the rate of change on the inside, the end of your system or organization is near. And a great way to start thinking about these concepts of time constants and taking it out from our classic control system theory and taking it into application to wider systems and organization is looking at the OODA, also known as the OODA loop, which was basically developed by Colonel John Boyd to understand a very particular problem. One, why American fighter jets during the Korean War had a success rate over their Soviet counterparts by at least a factor of 5. So first, let me tell you what those 4 steps of the OODA or OODA loop are. They are, first, observation. Are you able to recognize or see what's changed in the environment? This is also known as situational awareness. Now, this comes from obviously from things like temperature and pressure measurements, but they also come from our manager's experience and intuition when we're actually in a workspace. Once we've made an observation, then we get to orientation. So we take in an observation and we decide, is this where we want to be and what is our current state? And at this point, we're actually filtering information from the observation. And the danger here is that if we filter out some of the observation, we can actually fool ourselves that we're not in the current state that we're in. Now, of course, in controls theories, we write very mathematical algorithms, but this actually comes down to the decision-making process in people's heads when they go to orient themselves around the data they observe. And orient is actually an area where corporate culture plays a role because we tend to reject observations that don't necessarily meet our mental models about the way the organization is. So obtaining unfiltered observations that are relatively free of noise are critical in that we make a proper orientation prior to making a decision. So now we're at the decide step. We basically decided what our current state is based on our observations and orientations. Now we got to make a decision of what to do. And control systems do this very quickly and use concepts like models and digital twins and simulations to do that. But this also occurs in the management suite where people in the loop are making decisions based on those first 2 steps. And then finally, once we've been through those first 3 steps, it's time to act, which is take the best action based on the previous 3 steps. So again, John Boyd came up with this concept around looking at the performance of US fighter jets versus Soviet jets during the Korean War. And accordingly, the data indicated that the US fighters were 5 to 10 times as successful as their Soviet counterparts. You can see the photographs on the left. And this was somewhat of a puzzle because the Soviet aircraft had higher top speed, higher thrust, faster turning radius. It was essentially superior in every way, except for one. And if you look very closely at the canopies, the single advantage the American jet had was it had 360-degree visibility, particularly from the back. And what that allowed the pilots to do is, as the American jet went through its OODA loop, it could do a much quicker observation and orientation based on greater observability. After getting through those 2 steps, the pilot could then make a better decision. And even if it took the American fighter jet twice as long to act, it had picked up so much time in the first 3 steps, it would actually reach this deadline before its Soviet counterpart did, as we see in the photograph on the right. And why this is important for organizations, especially when they go to invest technology, is we tend to invest in technology that produces a rapid action, right? And what we really should be spending our time is investing in the technology that allows us to make better observations. And again, thanks to the fact that collecting and sharing data has dropped 2 to 3 orders of magnitude in the last 15 to 20 years, focusing on observation produces knock-on effects through the entire OODA loop and produces an overall time constant that's superior to sometimes investing in more expensive capital equipment around the act step. And just a brief note on orient. This is the most ambiguous step. And it's the step when we go to make our decision, our mental models come into play, both individually as a group. And this is where you'll see in decision-making processes that some information is rejected, such as this doesn't work for us. And what's interesting is now that we're looking at artificial intelligence and neural nets, which are essentially trained on large sets of data, when a new observation comes in, that artificial intelligence neural net could actually basically reject or de-weight that observation based on its long history. So what's fascinating is, although this was originally designed for explaining human pilot behavior, it actually applies to this new world of machine and deep learning as well. And one of the key parts about orient and in terms of the mental models is this great Henry Ford quote is, whether you think you can or think you can't, you're right. And this gets us into around culture change. So let's say we would like to change the way our model works. It turns out that to achieve this change in the system, you have to change its model. That's fundamental to traditional control. It's also fundamental to organizational behavior. And the way the traditional view works on retraining organizations is first we start by trying to change the people's minds through speeches, through education, through promising great results, and then expecting that the people in the system will then change their behaviors. And it actually turns out and has been validated through many academic studies, as well as practical ones, is that the real way you change that model of how the organization thinks is to first change the actions or way the work is done, then the mental models change, and then finally the culture changes. So a question to ask ourselves when we're looking at a current system and how it's behaving based on its model, whether that's a computer model or that's models within leadership's minds. The result is the same. And we don't change those models by explaining, we actually change it by providing that model new data, right? In the case of people, it's around having people do their work differently. And then around computers, it's around changing their data set to actually come up with a model that's actually more relevant to the current condition rather than what we've lost in historical conditions. And an important concept is, again, when we think of how any organization and system runs, it's really about whether the system's time constant actually responds more quickly than the environment demands. So when we look at organizations and how they behave, it's very critical to realize how long it takes that organization to react to an external stimulus. That's its time constant. And we can take that system time constant and break it down into the 4 steps of the OODA loop. And in most traditional companies, on the left, not a lot of time is spent in observation and not a lot of time spent in orientation. Where we get into trouble is we're now are sitting in conference rooms making decisions, and we start spending exceptionally long time in making decisions. And we're really speculating. And after about 20% of that time, the quality of the decision is not improving, but the time constant of the organization is actually growing longer. And then when we finally act, we've put in a long time delay. Now, if we actually improve the observe step, i.e. either we spend more time on the factory floor or we actually have superior real-time sensors that we can collect the data. That dramatically shortens the time spent in a decision. It also increases the quality of that decision. Then the action we take is superior. So we reduce the defects and negative consequences, but also we've given our organization more time to respond to the next external stimulus, which is represented by the dotted box. So what we're moving from on the left is an organization that spends most of its time in speculation to an organization that has balance between observation, orientation, decision-making, and acting. And technology helps tremendously here, primarily in that it provides companies and organizations with better observations by getting the data they need to the places where it's needed with rapid analysis. And the next concept in control systems is around chaos and stability. And this is was really pioneered by Edward Lorenz at MIT when he was, studying weather, and he built a relatively computer simulation of how weather behaves, and realized that a small offset in initial conditions, after running that computer simulation for several days, the results completely deviated from the previous result with a small change in initial conditions. Now, what does that mean for control systems? It means that perfect prediction just isn't possible, even in simple systems. And small deviations upstream lead to large, unpredictable, catastrophic events downstream. And the technology we have to actually make these improvements are, one, we can take much better real-time estimates of what our current state is, and then we can implement corrective feedback so that we're constantly resetting the state of the system so that these small errors aren't allowed to propagate into instability and chaos. And this is where the IoT is especially relevant because, as this great quote from Dirk Diskaskalu from Amazon, who's the VP of IoT, says, the IoT is really about knowing our current state, where everything is all the time. And now I'd like to show you an example of chaos in an Oklahoma oil field. On your left, you can see a typical natural gas rig, and it's basically it does two things. It drills for natural gas and oil, and it moves from site to site. And the problem in this system was that rig move between sites was taking 4 days plus or minus 2 days. That is a lot of chaos and noise. And we can actually look at that performance here. And you can see there's on the before state, as indicated by the red line, not only is the average about 4.5 days, there is an incredible amount of variation. And where this comes in terms of chaos and current state is after working with the team and making some observations, we realized that the team was unaware of how many rig trucks they were actually using as part of the move. They thought they were using about 12, 18-wheel rigs. They were actually using 30. And a subsequent experiment showed that only about 70% of the equipment they were actually carrying around was being used. So at least 10 of these 30 trucks were actually not only creating waste, but creating extra chaos on the Oklahoma oil field. So by essentially implementing technology that ranged from visual still cameras of the site and real-time video, but also remote monitoring and location of tools, we're able to reduce that chaos from 4 days plus or minus 2 days to 2 days plus or minus like less than half a day. So not only did this save about $15 million a year across the portfolio of 5 rigs, it actually significantly reduced the amount of variation. So therefore, downstream planning became much simpler. I'd also like to state that this had a tremendous impact on safety. the number one risk in an oil rig move, such as this, is basically collision of two vehicles, two moving objects. And if you reduce the number of 30 down to less than 20 and push it to 12, you are automatically removing a lot of that chaos. And when you remove chaos, you get an impressive result like this. Not only a productivity improvement, but you also see the risk drop. And then finally, it became a much more friendly system within people could do their work and both be effective at work and come home from work safely. That's an oil rig move. This example actually extends all the way to the entire supply chain. Jay Forrester, who founded the System Dynamics group at MIT, of which I'm part of, was asked by GE Appliances in 1958 this question: if the demand for refrigerators in their appliance factory is steady, why some months we're running full out with 3 shifts and other months we basically can barely fill 1 shift with enough work, when we know that's not the buying pattern of customers? So what Professor Forrester did over a weekend was set up a very simple simulation, essentially using paper and bingo chips to simulate this supply chain for refrigerators. And essentially, it had 4 steps within the actors within the supply chain: retailer, distributor, warehouse, and manufacturer. And there was time delays placed between all of those 4 actors in the supply chain. And this simple simulation, which has been conducted by tens of thousands of people, both at MIT and at other universities and institutions around the world, is that a small variation at the retailer is actually amplified as you move downstream, right? Now, in the supply chain industry, that is referred to as the bullwhip effect. But those of us who are control systems engineers know that this instability is caused by dead time in the system. And for any of you that have had the experience of working in supply chains, realize is there, just like this simulation, there are significant time delays in how information is passed between those 4 actors. And if we can leverage Industry 4.0 and real-time communication to reduce that dead time caused by poor information flow, we can significantly reduce the amplification that we see at the manufacturer through the supply chain, all through real-time information and eliminating dead time, which is a classic control system concept. And if we think about perhaps what is the most important principle behind the design of any control system, it's really around stability. Because if the system's stable, you can always drive up your performance until it becomes unstable. However, it's not enough that the control system engineer understands the nature of stability. There must be a way to communicate the basic principles of stability to everyone in the organization, because that will change their behavior and have them focus on controlling the response time of that system. So just as a relatively simple framework that control systems engineers can use to explain the role of stability and time constants in a system, you may find this helpful. First is when we look at a customer places an order, which is an order signal, and they give a deadline for that order to be fulfilled. And if they don't get that order by their deadline, they start engaging in behavior that's actually detrimental to the system, i.e., placing more demand on system production, which ultimately puts us into the beer game. Now, the way we avoid going into the beer game are also known as the supply chain simulation we saw previously with Jay Forrester, and avoid that bullwhip effect is to ensure that when the system receives the signal from the customer, it's able to deliver that result before the deadline. And if that result can be delivered before the deadline, i.e. the system time constant is less than the customer's time constant, then the system's stable. If the delivery time actually shifts out to be late, we're missing deadlines, this tends to destabilize the system. And the reason why this concept is important is most companies use an enterprise resource planning or ERP system to basically run their system. And it's based on standard response times to actually put out the schedule. And in most systems, the actual time constant has significant variation. And that's why in most companies, schedule completion rate is only about 70 or 80%, right? Customer on-time delivery. And there's a significant amount of destabilization in the form of expediting that results because of this lack of attention to the system time constant. And as a control system engineer, you can then start working with the teams to spend more time doing real-time analysis of what the actual system time constant is, rather than checking it every 3 to 6 months. And we're now seeing a trend that real-time cycle time information is actually being loaded into the ERP system in real time to actually provide real-time stability information. And now we're getting into the world where overall organizations using the ERP systems are acting like classic control loops. And it's all around getting that execution down to a precise standard. And the second way to buy time and improve the system's time constant is improve preparation. In most systems that involve humans working along capital equipment and machines, preparation is generally a weak point. And this typically turns up in the maintenance function or changeover function. And by simply investing in preparation, we can significantly reduce the system response time, and we can have a more stable system and serve our customer. So just sharing this concept that in stable systems, the time constant of the system must be less than the time constant that the customer makes a request is both simple and critical, and is a great way to communicate this information to your colleagues. Now, when we start to think about time constants and how systems behave, we essentially go from the classic world I come in, where chemical engineering, where we have fixed tanks of volumes, to the world where our fixed inventory is no longer fixed, and we can increase how much inventory we're storing based on work in process. And this actually is expressed by Little's Law, which is the fundamental equation for how operations work. It was named for John D.C. Little, who's a professor here at MIT. And what it says is the lead time, which here is represented by W, increases linearly with the amount of work in process. The reason why this is so dangerous is in most companies tend to build up a lot of work in process to serve the customer quickly. And what's not realized is in the short term, that actually helps you serve your customer. In the long term, having all this excess work in process actually slows down the system. And it's this concept that actually is what makes lean manufacturing so powerful, is by moving all this excess work in process, you're not simply saving your working capital, you've actually reduced the response time of your system. And the question is, well, then why do companies love to use work in process and hold so much inventory? Well, it has an extremely powerful benefit in any systems, in that it can absorb any sort of high frequency shock from the outside, shown here by this input. And then if you have large inventory, you can actually convert that high frequency signal, which our systems don't like, to a low frequency system plus a dead time equal to about the period of that sinusoid. So we naturally start to collect inventory and work in process to absorb high frequency shocks from our customers. That's a good use of inventory, but there's also a bad use when we're actually using it to absorb high frequency shocks that we've actually created internally to our organization. And if you've worked in any process or system, you will notice that most individual operators will store some work in process in front of their station in case, so they can keep their individual production rate up, with the negative effect that slows the system down. And this has a tremendously negative effect on the dynamics of the way our system behaves. So on the right, you can see a graph of measuring the distribution in response time for any system. So I may be producing automobiles, I may be producing an insurance form, and instead of everything spending an hour or 2 hours in the system, some will spend 25 to 30% more time there. And so the mystery is what it's actually doing in there. Well, it turns out that signal, if we take a closer look, actually indicates that our system behavior is not what we expected. And you will often see a distribution like this. So for instance, if we're, say, producing order forms or making automobiles, we would expect that the amount of time, or the time constant, would be relatively constant or fall into a tight normal distribution. And in fact, that's what we see here in this typical residence time distribution of systems and processes. Now, it's not that we can't get better by reducing that variation, but we also have other parts of this distribution that indicate how our system's working. Now, we may have some strong outliers. Those are special cause failures. And those, in my particular work, I don't typically worry about, because those go directly to the people who do risk analysis. And those are usually examined because their behavior was actually egregious compared to the normal behavior. When I look at most systems and the way they degrade, I look at the orders that are shown in number 2. And those are orders that, took 25 to 50%, maybe 2 to 3 times as long to come out of the system. And they often indicate that a defect in the system led to an item being held in work in process until it be fixed on. And that creates some serious problems because there was a customer waiting for that order. So not only did that order have to be reworked, which increased cost and on lower quality, because you can never make it, you can never improve it better than first pass quality, it actually inserted a time delay to the system. And as these hidden factories build up, our system's responses dramatically slow down. And as we do this, then we lose control of our system and we end up with catastrophic results, which not only include damage to the physical assets, but also involve such events as financial bankruptcy. I also want to talk about 4, which is some orders get through the system very quickly. Those are orders that the CEO or senior leadership usually asks for. And that has 2 problems. One, it pushes everyone else's orders back. And second, it gives leadership the false understanding that their system should be able to respond quickly at all times, when in fact, they've slowed down their entire system. And this probably looks familiar to you. And this is a great way to actually find those hidden factories and defects that live inside our system that actually distort the system's time constant. And this all relates to the classic concept of a value stream. If we follow a product through the order and we look at where that order spends its time, there's only 3 places. Was value being added to the customer during that time? Was that product or system held up so that the business can be improved, i.e. maintenance or operator training, or was that time wasted? So that's time that has value to no one, but those wasted time delays take a relatively short time constant and can increase it by the factor of 2 or 3. And that creates an incredibly destabilizing effect. And how do we control this? It's actually quite simple. We limit the amount of work in process in our system, and that's basically fixing our time constant. And so the question we need to ask is, what's a minute worth in our system from the customer perspective? And is our system capable of making that need? Now, I want to show you a classic way of how we can actually control the system's time constant by controlling the work in process. And that not only applies in chemical plants where tank levels are fixed, but it applies to any system. And it really gets to this concept of Kanban. And to explain it very simply is we're all in the phenomenon in this COVID world where we want to limit the number of people in the store. So you see in this photograph on the right. And the way we can actually control the amount of people in the store or the work in process is to actually limit the number of carts. So once the carts are exhausted, no more people can enter the store until a cart is retrieved. And it's this basic concept of creating a limit on the work in process actually results in a time constant that remains under control and protects our system from going unstable. And as we start to approach the end of this talk, I would like to now step back and think about how these concepts can apply for a control systems engineer and help explain those system concepts and apply them to the greater organization. We are now in an era where data-driven organizations are considered leading we're now in an era where data-driven organizations is where most companies are looking to. The challenge with that is it's not simply data. What they're really looking for is a specific type of data. And it's best summed up in this three-step framework, which is very similar to control systems engineer, said any system consists of three parts: the model, the process or the system, and the data. And the model produces what we think should have happened. The process or system produces what actually happened. And the data we're looking for, and that's most valuable to collect, is the difference between what we expected to happen, which is the model, and what actually did happen, which is the process. So now you can see the reason we're collecting data is so that we can use it to produce a negative feedback loop. And this can be very instructive to help companies first determine on what data they should be collecting, and two, how do we actually implement that data so it produces value for the organization. And there is a role of the model in control design. All controllers are based on a model, which was work first discovered by Ross Aspey in the early 60s. And in the 1980s, the role of a model in a feedback control loop became explicit through the work of Manfred Merari. And the better our model of the system, the faster and better performance we can get while maintaining low risk. So understanding that having a high fidelity model is critical to performance and operations is really key when we're not only trying to control classical traditional operations, but extending it to the organization as a whole. And with that, it's instructive to think about where some of these concepts came from. And we always, as control engineers, recognize Laplace in his role of Laplace transforms, but he was also famous for Laplace's demon. And he spent a lot of time trying to get the initial conditions exactly right so that the entire future of the system would perform in a clockwork fashion. Thanks to the work of Edward Lorenz, we know that that's no longer possible. But even early on, this was apparent to Napoleon. Now, again, we're probably familiar with Pierre-Simon Laplace for his control system theory. You may not have known that he was Napoleon's artillery instructor. So obviously, it's very important to get your initial conditions correct because you no longer had any control elements on the typical artillery of the day. And when Napoleon actually took over as Emperor of France, he hired Laplace as the Minister of the Interior, and he fired him 6 weeks later because Laplace spent so much time trying to get the system correct initially, they never went into action. So first, what we've learned is we need good preparation, but we also need to act with agility. And finally is Euler comes into the picture, because whenever we preparation then act, we're always going to have some deviation. That's negative feedback. When we have negative feedback, we make an iteration, which is exactly what the Euler's method did, and leads us to this classic quote from Laplace: read Euler, he is the master of us all. And then as we wrap up, our real last point is we're trying to build a control system, not simply for physical devices, but for an entire organization that also contains people. And we actually do have a formula for behavior, and it comes from Kurt Weil, who did this work at MIT in the mid-40s. And he recognized that the behavior we observe in any system is a function of the people and the system that they find themselves in. And if we simply try to change people's behaviors or replace the people, we won't actually change the behavior of the overall system, because that hasn't changed. And this is where technology can play an important role. Technology, in the form of better real-time information, actually can change the system, which then changes the people's behavior, and we get this virtuous loop. Exactly what we saw in the example with the Amsterdam Canal. And so recognizing that technology can be used to impact and improve the system, which then leads to people's behavior changes, is an exceptionally powerful way to introduce technologies into organizations with people. And so one of the classic things we've learned in control systems is system identification. Now, in the classroom, we normally provide lots of time series data. That is exceptionally useful. And of course, now we have much more of it, but we can also use this in any system that contains people and workers. And it works like this. The first step is prepare the system for execution as best as you can, right? Next, run the execution. And as you make observations of defects, catch them quickly and correct them, right? Now, that's normally known as a workaround, but if we're scientific about that, if we get enough of those corrections, we actually adapt. And then the system changes through preparation and observation. So what you're seeing here is a feedback control loop implementation of classic control theory in an organization that contains humans. And how Industry 4.0 can help us with this is it provides us with many, many tools that are actually enhanced through better observations. That's both through better sensors, video, and character and picture recognition. It's also in faster running algorithms, and it's also in reducing the lag time between when data is collected and when it can be provided for real-time feedback. So just in summary, all systems are really time machines. A customer comes to our system for us to produce something faster than they could on their own. And that time has an exchange rate. In order to produce value for the customer, we have to use our time effectively. And if we design a good system, it will allocate our time so that the customer gets a good exchange rate on their time. Now, when the system needs more time, when it can't keep up, it first starts to borrow, then it steals from the system. And the signal from that is you start building up work in process inventory, which will ultimately destabilize the system. If we have better observability and better measurements of the current state of our system, we can address these slow degradations that ultimately lead to disaster, and also serve our customers faster in real time, which gives us better margins. The Toyota production system is the closest implementation of this design, but what's exciting now is Industry 4.0 allows organizations to incorporate these concepts with less discipline if we understand the control system principles. So with that, thank you for this presentation, and Mark, turn it over to you.
Thank you, John. Here are reminders about the attendee experience for this session. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within the session, click on the left panel labeled Notes to do so. Get your questions answered by participating in the live Q&A following the presentation. Want to take the session again? No problem. The session will be available on demand. If you're experiencing difficulties, please log out and back into the session to continue. Thanks again to Dr. Carrier, Senior Lecturer, MIT Sloan School of Management, Systems Dynamic Group. Please see the link for additional information from Dr. Carrier. I'm Mark T. Hosky, Content Manager, CFE Media and Technology. Thanks for joining us today for this CFE Media and Technology education session, Applying Control Concepts to the Adoption of Industry 4.0, sponsored by Honeywell.